Last time we managed to talk to the Klipper MCU by using the Klipper console. However, we weren't able to move the stepper as we didn't know its OID, and we weren't able to configure it ourselves as we weren't able to compute the checksum manually. Now let's talk to the MCU from our code. Even though the Klipper protocol is pretty well documented, we can just reuse Klipper's SerialHDL class for handling the serial. To do so, we first create a new file, in this case inside the Klipper folder, just for ease of accessing the other files, and we will need to import the SerialHDL library, which will handle the serial connection. This requires the reactor runtime. This is the main synchronous runtime Klipper uses for all of its parts. This basically allows synchronous single-threaded multitasking. We will just for convenience also import clocksync, which lets us know the current clock time on the MCU synced over the serial protocol, including latency compensation, and we will import zlib for computing the checksum for the config. The basic structure of this file is that we will first create a new reactor runtime. We will then initialize a serial handler as well as a clocksync object. We then need to put our code in a callback function, which will then be run in the reactor runtime down here. So we have the callback, which will contain all of our code. This will allow our code to seamlessly hand over control to the SerialHDL process, running in the same thread but through the reactor in more or less parallel. We will first open up a connection to our printer using the same serial port and baud rate we used the last time. We can now also get the message parser. This will allow us to pass response. Then we'll initialize the clocksync object connected to the serial port. This will give us the real-time time on the microcontroller. And now we can start working on the config. We have the pins for the stepper. In this case, I'm using the x-axis stepper on the Prusa. We will also need an enable pin, as by default the Prusa steppers are not enabled, so you can freely move them. So we will need to enable them first before we can use them. From there, we will get the microcontroller frequency. This board runs at 16 megahertz, but we can just get this from the message pass. We will use these for calculating timings and speed. Now we will calculate how long to have the step pulses. A good value is 5 microseconds. That should be good for pretty much any stepper controller. Some can go down to steps of just 1 microsecond, but 5 should be a pretty safe bet. Here now we define some OIDs. Our stepper will have the OID 0 and the enabled output will have the OID 1, giving us a total of 2 OIDs we're allocating. Then we can start configuring it. Like previously discussed, the MCU starts in an unconfigured state. You first tell it how many OIDs you will need, and then you tell it what those peripherals are. So we first tell it to allocate 2 OIDs, then we will tell it to configure the stepper with the OID 0 and the step and direction pins we've previously defined, and then we will configure the digital out for the enable pin. From here we will put them all together in a single string and calculate the checksum. This will be the checksum we will transmit along with the configuration, so the microcontroller knows it has received everything correctly. From there we will send the actual messages, the message to allocate the OIDs, the message to configure the stepper, and the message to configure the digital out for the stepper enable signal, as well as the finalize config command with the checksum we've previously calculated. Now the MCU is in a configured state and we can enable the stepper enable pin. From then on we just do some calculations about how far we want to move. On the Prusa, the millimeters per rotation is 32, which is stepper of 200 steps per revolution times 16x microstepping. So we will have those to calculate the step distance in millimeters, take a target distance of, in this case, 50 millimeters, and calculate the number of steps needed to do so by calculating the target distance by the millimeters per step to get the step amount, which we then round up to the next integer. Also take the speed, which will be the interval in the NQ step function. I'm going with just 2 millimeters a second since we will not be having any acceleration, so it's a pretty sudden start, and I don't think the stepper motor drivers are configured with a particularly high torque when they're in an unconfigured state. From here we get the current microcontroller clock from our clock sync, and we will calculate the start time. We will just take the now time plus 2 seconds in order to allow us to have some time to transmit the messages. The stepper motor normally just operates on a queue, but when the queue is empty we will need to tell it when the queue starts. This is very useful if you want to synchronize multiple access together, so you can queue them up at the same time to start. So we just give it a start time, send it that we want to queue the steps we previously calculated. From there we can already end our reactor, since this will exit the program and we will have sent every message we wanted to send. We'll also have the return never, which is just telling it that this callback is not periodic but just a single time callback. If you wanted a periodic function, you could give a different return type here. Yeah, that's about it. So let's try this. I will first stop Klipper again. I will reset the microcontroller so it's in an unconfigured state. Right now the motor is turned off and we can just position it here. And now we will run the command. We can see it moving very slowly. We have now successfully configured the MCU from our own code and commanded it to do our first moves.